Today we are going to talk about four common discrete random variables, and then we will continue to the continuous random variable. Last week we just mentioned discrete random variables, and then here we have four. And sometimes you will use that a lot. The discrete random variable. The first one is called Bernoulli random variable. What is Bernoulli random variable? And also that when you've done those common random variable, then you need to know how do you express the PMF and what is the expectation and also the variance. So for the Bernoulli random variable, the PMF is either 1 minus P or P. Bernoulli means that here it is you only have two choices, either head or tail, or 1 or 0, or on and off. So that will be Bernoulli. Okay, so either 0 or 1, head or tail, on and off. And then this P is called the Bernoulli parameter. And we will write in this way, X for Bernoulli with P. That means X is drawn from the Bernoulli distribution with the parameter P. And you can find the expectation, that will be P. Pretty easily, 1 times P and 0 times 1 minus P. So you get P. And the variance will be your multiplication of the PMF. Okay, that is Bernoulli. And based on Bernoulli random variable, the next one is called binomial. For binomial, you can think of binomial random variable as sum of n Bernoulli random variables. So here it says, I have I1 to In. Those are the sequence of Bernoulli random variables. So I flip the coin. First time I flip the coin, and then I also flip the coin. I flip the coin n times. And once I have another random variable, X is the sum of this Bernoulli random variables. This X become binomial. For example, if I flip the coin 5 times. So if I flip the coin 5 times, what is the probability of having 3 heads? 5 times I may have head, or head, or the last one maybe tail. Well, 5 will have so many results. So how about just 3? So if I flip the coin 3 times, so I may get either head, tail, head, or even head, tail, head, tail, head, and tail. 8 possibilities. Okay, 8 realizations. So if I flip the coins 3 times, what is the probability of getting 2 heads? And this. Okay. So each time I'm doing the Bernoulli, but if I sum this together, it becomes a binomial. Okay. So binomial like n choose k. Okay, n choose k. Like 3. I flip the coin 3 times, and then what is the probability of getting 2 heads? So 3 choose 2. All right. Again, I may have head, tail, or head, tail, head, or tail, head. So I 3 choose 2. That'll be 3, right? I will get 3 I'll get 3 realizations that matches our requirement. So PMF is here. N choose K. And then to get in the head, I get P tail 1 minus P. Okay, so I have two times getting head, 1 time getting tail. And as I said, this is Bernoulli. Here's Bernoulli, right? Because I have a head P and tail 1 minus P for their PMF. And then here this P is also the parameter. It's called binomial parameter. And I also have an N. And N is the total number of states. Okay, I just throw the coin 3 times, 5 times, or I send the signals is either 1 or 0, and I send it 100 times. That'll be your N. And then we write it down as binomial N and P. So if we say this is a binomial random variable, then we need to know the N and the P, the total number of states, and also the binomial parameter. So X is drawn from the binomial distribution with the parameter P and of the size. So you can also think about N is a size. We can also prove that the expectation is the size times the parameter P. So how do we prove this? Based on the definition of expectation. Let's review this. For expectation, what is the expectation? I consider all. So can consider all possible outcomes, possible realizations, xk, times their corresponding weightings, the PMF. Okay, now let's bring the PMF here. It'll be K, N choose K, P to the K times 1 minus P, N minus K. Alright, and how do you find the summation? You may change variables. Okay, but it looks like you can do it, but a little bit complicated. So let's do another way to prove this. So since we say that binomial random variable is the sum of binomial random variable is sum of the n Bernoulli random variables. So we can think about, and also we have the random variable x that equals, this is Bernoulli, this is Bernoulli, this is Bernoulli, and this is binomial. So if we think x is I1 plus I2 till In, then how about the expectation of x? Right hand side, there will be expectation of the first Bernoulli random variable, and then the second, the expectation of the second Bernoulli random variable, and so on to the last, the expectation of the n Bernoulli random variable, the nth Bernoulli random variable. Each time, we know this is P, and here is also P. So I have MP. Okay. Similarly, then let's do the variance. For the variance, that'll be variance of the first Bernoulli random variable plus the second one, the variance of the second Bernoulli random variable, and then till the last one, the variance of the last Bernoulli random variable. And we know for the variance of the Bernoulli random variable, that is p times 1 minus p. So here is also p times 1 minus p. Then I have n times this p times 1 minus p. So np 1 minus p. Okay, so now the next one, geometric random variable. For geometric random variable, it says that physically the geometric random variable defines a sequence of Bernoulli random variable. Again, we will use Bernoulli random, the concept of the Bernoulli random variable, Bernoulli trials, and with k minus 1 consecutive failures followed by the one success. So it's like I flip the coin and I always got tail. And finally I got head because I want head. Then this will be the geometric random variable. What is the probability of getting the head when I throw the coin? The first k minus 1 times are all tails until the kth time it is head. Then overall this is the geometric random variable. So I always want to get head, so I just flip the coin. If it is not head, then I keep going, keep continuing to throw the coin until I get the head. So the k minus 1 times it is tail, and the last one is head. So this PMF is easier to interpret and remember. Okay, k minus 1 is failure, and then the kth time, so that will be p. And p is called geometric parameter. And we also write geometric p to say that x is drawn from a geometric distribution with a parameter p. And the expectation is 1 over p. Variance is 1 over p, or 1 minus p over p squared. Let's prove this. The expectation. The expectation, again, let's consider all possible outcomes, that will be k, times the corresponding weightings, the PMF of the random variable. And here is geometric. So we have p, k times p times 1 minus p to the k minus 1. Okay, so this time we can put p outside because we do the summation for k. And for this summation, it's an infinite summation, so because you probably never get head. So you are so lucky that you always get tail. So here will be 1 divided by 1 minus 1, the ratio squared. That gives you 1 over p. So we can recall this summation. K from 1 to infinity. K times the ratio to the k minus 1. That is 1 over 1 minus r squared, the ratio squared. The next one is Poisson random variable. This is also very common, and you will use Poisson random variable in communication. So what is Poisson random variable? X is a Poisson random variable. Then the PMF is in this form. The Poisson rate to the k divided by k factorial times e to the minus lambda. And this k could be from 0 to infinity. We say x is for Poisson lambda. That means x is drawn from the Poisson distribution with the Poisson rate lambda. For this Poisson random variable, the expectation and also variance are all the rate lambda. We assume Poisson distribution for queuing. If you line to, for example, the McDonald's, the customer's line, and then you can assume that people coming as a Poisson random variable. Let's first verify the expectation. So why the expectation is just lambda. For the expectation, consider all possible outcomes times their weightings. That is k from 0 to infinity, k, and then the PMF, Poisson rate to the k, divided by k factorial, e to the minus lambda. Since e to the minus lambda is nothing related to k, so I just put it outside the summation. K from 1 to infinity, lambda to the k, divided by k minus 1 factorial. Now, how do we deal with this summation? So we just change the variable that k prom equals k minus 1. So in that case, the expectation is e to the minus lambda. And now I have k prom. Okay. Here should be k prom. K equals 1 to infinity means k prom from 0 to infinity. Okay. And then lambda to the k becomes k prom plus 1 divided by k minus 1, that's just k prom. So k prom factorial. So that will be e to the minus lambda, k prom from 0 to infinity. I have lambda times lambda to the k prom divided by k prom factorial. Okay, and again I can put lambda outside. And this time I just want to put the exponential part inside the summation, and let's see what is this. Lambda to the k prom divided by k prom factorial times e to the minus lambda. Now, what is this summation? Lambda to the k prom over k prom factorial e to the minus lambda. This summation from 0 to infinity. What is this? What is the result? You will also see that this is the PMF of Poisson random variable, right? So if this is the PMF, then what is summation k the PMF. If we sum all the PMF, then from the property of the PMF, this is 1. This is 1. So that's why it is just lambda. Okay. So based on those 4 random variables, let's see some examples. So first, suppose that in World Cup 2018, I would like to find the probability of Cristiano Ronaldo. Okay, so he does the hat trick in one game. Okay, suppose we know that probability, Cristiano Ronaldo okay, does the hat trick in one game. This is the event. Okay, so here I have curly brackets. This probability is 30%. Suppose. Okay, for this statement, that also implies one thing. That is, according to the property or the axiom of the probability, that means no hat trick for one game is 70%. Because overall it's 1. It should be 1. And if we play 10 games, then what is the probability of Ronaldo has 3 hat tricks? So now we only know for one game, he has the hat trick, that's 30%. Now if I play 10 games, then what is probability of having just 3 hat tricks? So you see here, this means either you have hat trick or not, like yes and no. Or you can think about this 1 or 0. I only have 2 results. So for this one, this is the Bernoulli. Okay, yes or no. Okay. Now we do this yes or no for 10 times. So for 10 times, I want to know over this 10 times, what's the probability of like getting just 3 hat tricks, just like 3 yes. So in this case, based on 10 times, I got 3 yes. The Bernoulli random variable becomes binomial or geometric, because here we have 2, right? Based on the Bernoulli, we have binomial and also geometric. But this one is not just talking about, oh, I always fail until I got success. So this becomes binomial. So here we can have the binomial PMF. N choose k, p to the k, 1 minus p, n minus k. So you get 10 over 3, because I only want 3 hat tricks. And to get the hat trick in one game, there will be 30%. And if not, there will be 70%. So you got 0.266. So maybe it's around 27%. Okay, now another example, since we talked about Cristiano, then how about the Lionel Messi? So this time, Lionel Messi, the probability of getting goals in penalty area. So Messi goals in penalty area. Say that's 40%. This also implies what? If he missed the goal, missed goal will be how much? 60%. Right. So again, it's either in or out. So two possibilities, yes or no. Okay, so there'll be Bernoulli. Now, this is a Bernoulli random variable, but here we define another random variable. This random variable is the number of times when Messi first goal successfully. Okay, so for the first goal successfully, that means maybe the first 5, it fails, it missed the goal. Maybe the first 7, 10, 20, and then finally he goes. So the PMF will be the first k-1 times they missed the goal. The last one he goes, so there'll be P. So suppose I want to find that the k equals 12 of x. 12 means the first 11 times he missed the goal in penalty area. And then in the 12th time he goes, so first 11 times that'll be 1 minus p to the 11. The last one is p. So here we have 60% for missing the goal, 11 times the last one, the goal, 40%. So this probability is pretty rare, but we just randomly make the number. Okay, so here's an example of binomial random variable and also geometric random variable. Last one, let's see the Poisson random variable. They normally use the telephone call center, or like a customers lining up to the counter. So here we say that average phone call arrival rate is lambda. And then the random variable x is the number of calls. I want to find x, the probability of x greater than 4 calls or less than or equal to 5 calls. So like in the telephone center, you may get a phone call, and what's the frequency? That's the arrival rate, lambda. Okay, so during a certain time, I get probably 5 calls or 3 calls or 6 calls. Then I want to find the probability, getting less than 5 calls or greater than 4 calls. First, the probability of the random variable greater than a certain number, say 4, that also means this is equal to 1 minus probability of your random variable is less than or equal to 4. Right, from the probability axiom. What does that mean? X is less than or equal to 4. So during that certain time, the number of calls is less than 4. Less than 4 because means that it's either 1 call, 2 calls, or 3 calls, or 4 calls, or maybe 0 calls, right? Because it is discrete. You get a phone call, either 1, 2, 3. You cannot get 1.5 calls. Okay, so this means I'll consider maybe there's no call, or maybe I have only 1 call, or I just get 2 calls. Okay, so this part, consider the x from 0 to 4 will be 1 minus k from 0 to 4 lambda to the k divided by k factorial e to the minus lambda. Well, it also shows that if I want to find the probability of the number of calls is less than or equal to 5, then it is just mentioned k from 0 to 5 lambda to the k over k factorial times e to the minus lambda. For the partial random variable and also binomial random variable. For the binomial random variable, we have the size n and also parameter p. And then when p is very small and the size is really, really big, then the binomial will become partial. So here, partial approximation for binomial. So n choose k, p to the k, 1 minus p to the n minus k. They will converge to lambda to the k, k factorial, e to the minus lambda. And this time the lambda means np. Okay. This is only valid only when p is very small and n is large. Okay, so now we just introduce 4 common random variables, discrete random variables. Let's just have a summary. First, what is Bernoulli? Bernoulli means I describe either success or failure, heads or tail, for just one trial. Yes and no. Right, so we describe either success or failure for one trial. Only 2 possible results. And then the PMF is here. Then the expectation is P, and the variance is P times 1 minus P. For the binomial, I'll describe the number of success in n independent Bernoulli trials. Okay, now I consider n independent Bernoulli trials, and how many numbers do I have for success? How many times do I success? So it describes the number of success in n independent Bernoulli trials. So in n trials, the PMF is from n trials, how many times I success, and choose K. And each time when I success, the probability should be P. So P to the K, and the probability of failed 1 minus P, I have n minus K times. And your K is from 0, 1, 2, till n. The expectation is NP, and the variance is NP times 1 minus P. For geometric, I describe the number of trials until the first success. In the sequence of Bernoulli. I still do the Bernoulli trials, but I would do it again and again until the first success. Then the PMF is I only have one success, so it's P. And before the success, I failed for k minus 1 times. And k could be from 1 to infinity. The expectation is 1 over p. Variance is 1 minus p divided by p squared. And for the Poisson, the PMF is lambda to the k divided by k factorial times e to the minus lambda. K is from 0, 1, 2 to infinity. And then the lambda should be greater than 0. The expectation is lambda, and also variance is lambda. And we can approximate binomial PMF. Binomial PMF. When n is large, and then p is small, and also the lambda is n times p. Alright, so now let's continue. After knowing the discrete random variable, let's talk about the continuous random variable. It's pretty similar, and we can quickly go through this. But for the continuous, that means my sample space becomes continuous. So sample space becomes continuous. For example, like my sample space becomes time or the area. So how do we move from the discrete to continuous? For discrete random variable, it is a sequence of delta function. Okay, we can think about the discrete random variable is a sequence of delta function. Like, here's my x. I have x1, x2, x3, x4, this PMF for discrete random variable, PMF is probability. Okay, but later on, for the continuous, is a little bit different. But here, let's just remember, for the PMF, that is probability. And this x1, x2 to sk, or this x, lowercase x, to sk, or even more. This is a countable set. And here for the countable set, the countable also means This also includes the infinite series. Say 1/2 to the k, like that. Okay. For discrete random variable, the realization it is a countable set. Now, for the continuous random variable, it has uncountable set of values in the sample space. Here becomes uncountable. And we can plot, instead of saying PMF, it's called PDF. And we will mention PDF, introduce PDF right away. So from L to U. So the probability becomes, I want to find the probability between X and U. I cannot just find 1 point, 1 point, 1 point, 1 point. It should be a range. So when we learn each random variable, we need to learn their PMF for discrete random variable, PDF, and their expectation. For continuous random variable, we say probability density function rather than probability mass function. For probability mass function, it is just probability. But let's see, probability density function, what is this? The PDF of a random variable x, it is a function. Okay, we say density function, so it is a function. That function yields the probability of obtaining this random variable between a and b. So I will integrate it over the interval a and b. See the math expression, f of x. That means f of x is not the probability. Okay. So for the probability density function, it is a function, not the probability. But I can find the probability of this random variable between two numbers a and b. How do we find that? We need to use the density function and do the integration from a to b. So if x is continuous, we know probability of the random variable between a and b. This is the PDF, and I do the integration from a to b, which means what is the probability of x equals certain point like x naught? What is this probability? We need the integration, right? If it is just one number, then for the integration, that'll be 0. So if we plot the PDF, it is from A to B. So this is the area. For continuous random variable, for 1 point, I don't have the probability for the random variable just equal to 1 point. Okay, because if it's just 1 point, what is the integration? There's no area. It'll be 0. But if x is discrete, so if x is discrete, let's plot . . say this is the PMF. Maybe this is X naught, and I still have A and B. Here's A and here's B. Now I want to find the probability of the random variable between A and B. Between A and B, so between A and B, I only have a value at X naught. So this is equal to probability of X equals X naught, and which is the PMF of X naught. You can also think about this as the integration from A to B. We still have Px x and times the delta function x minus x naught. You may think of this as a PDF. For this part, if you take the signals and systems, well, if not, that's fine. Or for the mathematics, engineering mathematics, we know the integration of the delta function is 1. So if I can do the shift x times delta x minus 5 dx. I only have values at x equals 5, so this is 5. This shift to 5, and I have an impulse. So now let's see the properties of PDF. There are some good properties for the PDF, and we will use that a lot. Like the first one, if I do the integration of the PDF, then there will be 1. So PDF means probability density function. So if I consider all this density function, do the integration, calculate the areas, overall it should be 1. Because when I take the integration, see here, when I take the integration, it will be the probability. So this value definitely cannot be greater than 1, right? Because it is probability. And you only consider A to B. But if you consider everything, overall from the probability axiom, it should be 1. Right, you consider all possible probabilities together. Like this will become a sample space. Then the probability should be 1. And also the density function should be greater than 0. And we know that how do we find the probability? So for example, if I say that this is a valid PDF, then I need to find the constant C, or the variable parameter C. So if it is a valid PDF means if I take the integration of this PDF, it should be 1. X is from -1 to 1. C or minus x squared. This overall is cx minus c times 1/3 x cubed. X is -1 to 1. So this should be 1. Then you can get c is 3/4. Now, since PDF is not the probability, okay, we need to do the integration, then it becomes probability. But do we have any other term I can just express to say that this is the probability? Yes, we have this called CDF, the cumulative distribution function. Here is the definition. The CDF, just the probability. Like in discrete random variable, the PMF is the probability. Now for the continuous random variable, CDF is the probability. The probability of the random variable less than or equal to some certain point x. Okay, make sure that you know this x and also this lowercase x. And this probability is to integrate your PDF from -infinity to this x. So which means this x can be changed. You can say this is y, and then I will integrate this to y, or to any sample. So the CDF of continuous random variable and also the PDF, they have the relationship. So if I have the PDF and the CDF, when I take the integration, take the integration of your PDF, then that is your CDF. Which means if I take the derivative of my CDF, then that is the PDF. So since PDF will have some properties, of course for the CDF, we also have some good properties for that. First, let's see. The CDF of x, f of x, means that I will do the integration from -infinity to that certain point x. I can change it to z. It is just a number, okay? So if I say that the CDF of infinity, here I put the infinity. So if I put the infinity from the property of the PDF, this should be 1. Okay? So here, because or you can just buy the definition. The definition of the CDF here is fx dx, and by the property of the PDF, this integration is 1. And then we can apply that to the second one. The CDF of -infinity is 0, because if we have put -infinity, get -infinity to infinity for the integration of minus. So of course it is 0. Then based on the first and second properties, then we know for the CDF it is between 0 and 1, which is also reasonable because what is CDF? CDF is probability. The probability definitely should be between 0 and 1. Okay. And then CDF is non-decreasing. Okay. Why it is non-decreasing? See this integration? You will always accumulate something, right? If you plot the PDF first, so here's the PDF. So maybe your PDF is like that. And you want to do the integration. So suppose this point. So here the CDF part like this. No. This is X. So now, since your PDF is greater than or equal to 0, and we increase the X in PDF, increase the X, we get more areas, right? Under this PDF, these areas will be your CDF. So if I increase the X, my integrated values also increase. So now, how do we find the probability of X is between A and B? We can use the PDF, but we can also use the CDF because CDF is the probability. So here there will be a CDF of B minus the CDF of A. You can also think about the integration from minus infinity to B of your PDF dx, and then minus another PDF this subtraction will be equal to the integration of from A to B times the PDF. This is the CDF of B, and here is the CDF of A. From the properties number 3 of the PDF, this probability is equal to the integration of my PDF from A to B. But the integration from A to B, we can rearrange this to a subtraction. So for this equation on the left-hand side, the first part will be the CDF at B, and the second part will be the CDF of X at point A. So we can either find the probability using the integration with the PDF, or you just have your CDF do the subtraction. And you can see that the CDF is non-decreasing. Okay, going up. Non-decreasing, that means sometimes it can be flat, and still go up. Okay, and from 0 to finally that should be 1. So in this case, then CDF is right continuous. So what is right continuous? First, let's see left continuous, right continuous, and also continuous. Left continuous means here. Left continuous, that means at this point, there's a point H. Here is f of b. And here is f of b minus h. Okay, when h goes to 0, they will close to the function at b. Okay, so they will get closer to f of b when h goes to 0. Then right continuous means I have a point at right. So if I have a point at right, say this is f of x at b, and here is f of x at b plus h. So they will also go closer to f of b, but they will go closer to the left. So h, when h goes to 0, they will close to the point on your left. But the right continuous means that I have a point at the right first, but they will go closer to your point in the direction to f of b. So here we can also write then I have a right continuous and left continuous. And of course, we have continuous, just call continuous. That means no matter your point is right or left, they will all converge to your point when h goes to 0. And which means these two should be equal. Okay, now the next one. Then what is the probability of x equals b? For the continuous, we know it should be 0, right? Because we don't have a point. We don't have a probability at just one point. But sometimes we may have, because it is not, at that point it is not continuous. If it is continuous, the probability should be 0. If not, then there will be your CDF B minus your limit. Okay. This happens when you have this case, so this is f of b. At this point, because b minus h, so it's left. When h goes to 0, so they will get closer to UFB. And now here I have a gap. The probability of x equals b. This is just the probability of x equals b. Okay, and this probability is the height. The height of the gap. This height of the gap determines the probability. Of this discontinuity. Discontinuity. Only when I have a discontinuity, then I can have the probability at that point. Okay, and that probability will be just the height, the gap, the height of the gap. And here, since here we also have in the notes, if fx is continuous at point B, then we know continuous, it should be equal fx at B will be equal to limit h goes to 0 when the point b minus h, and then h goes to 0. So here we get the result. The probability should be 0. And then sometimes we also may need to find the probability of x is greater than some point. Still using the probability axiom. And this is 1 minus the probability of x less than or equal to some point. Every time now you see this expression, probability of your random variable x less than or equal to some certain point, what is this? This is our CDF. Let's see this example. I have our CDF. When x is less than 0, that's 0. But when x is greater than 0, I have this equation. So first, let's plot this CDF. Here's 1. And here is 3/4. So it's so small. We can plot that a little bit bigger. So here's 1, here's 3/4, When x is less than 0, it's all 0. Oops. Maybe all 0. Until x equals 3/4. They'll go to 1. Because when x equals 0, you plug 0 here. So it's 1/4. 1 minus 1/4 will be 3/4. Okay. Well, why this trend? Let's see, for e to the minus x, we need to know e to the minus x looks like in this case. So 1 minus the exponential to the minus x, they'll be the other way. So that's why for this equation, it looks like this. Okay, so now I have the CDF. I want to find the PDF. How do I find the PDF? For the CDF and PDF, we know that if I take the derivative of your CDF, that is the PDF. So let's take the derivative of our CDF now. df over dx. It's 1 minus 1/4 e to the minus 2x. That is 1/2 times e to the minus 2x. But we need to see, now the CDF, it is continuous, but I still have a discontinuity at 0, x equals 0, and here's a gap. And we know that once we have a gap, at that point, which is 0, I should have a probability. So I should express that. So first, when x equals 0, it should be the CDF of x at 0 minus the CDF of some point on the left, and then that goes to, for h goes to 0, so they approach to the origin. This is also 0 to the left. So you have 3/4 minus 0, you get 3/4. So now you can write it down, the PDF. When x is less than 0, you take the derivative, it is still 0. So here is still 0. When x is greater than 0, then we take the derivative. It should be 1/2 times e to the minus x. But we also need to consider x equals 0. So 3 components. First is x is 0. X less than 0, the answer is 0. When x equals 0, then it should be the probability of x equals 0. Otherwise, I take the derivative for x greater than 0. So it should be 0. And when x equals 0, that should be 3/4 times the delta function x minus 0, or 1/2 e to the minus 2x, or x is less than 0. When x equals 0, that will be 3/4. When x is greater than 0, there will be 1/2 times e to the minus x. We can also write this in another expression. It's 3/4 delta function plus the unit step function, 1/2 times e to the minus 2x u of x. Here we need to know what is the u function. For the u function, that's either 0 or 1. So when x is greater than or equal to 0, there will be 1. Otherwise, it is 0 all the time. And we can plot the PDF. So when x is less than 0, it's all 0. When x equals 0, it's 3/4. And then later on, there'll be the exponential going down. Right? So those are the properties of the PDF and the CDF. So the next one is the expectation. So same concept. What is the expectation? I consider all possible outcomes times their corresponding values. So for the continuous case, all possible becomes the integration. All possible outcomes x, the corresponding weightings, the PDF. So x times f of x dx. And then for the expectation of a function of continuous random variable, still consider all possible or functional outcomes times their corresponding weightings, which is the PDF of x. And the variance is just the x minus the mean. This should go with expectation, okay, for the continuous case. And also because for the variance, we know the variance is the expectation of your random variable minus the mean squared. So that's why this is also another expectation, right? So same thing times their corresponding weightings. You can consider all. For example, from the previous one, this random variable, continuous random variable, I want to find the expectation. The expectation is from minus infinity to infinity. I consider all possible outcomes times the weightings. So I only have values once x is greater than 0. So it's from 0 to infinity. And the x and the PDF 1/2 e to the minus 2x dx. And at 0, I have 3/4. And from minus infinity to 0, I have x times the PDF. PDF is 0. So this gives you 1/8. The next example, I have a CDF, and now I want a PDF. So I want to find a PDF. For the CDF, we can also plot at first. So my x will be from 0 to 1, 1 to 2, 2 to 4, and greater than 4. So there you go. So I should have 0, 1, 2, 3, 4. Here's the x. Here is the fx. I have 0, 1, 2, 3, 4. 1, 2, 3, 4. And I have 0.2. And 0.7. 0.9. And 1. My PDF, oh no, my CDF is green. Okay, let's use green. X between 0 and 1, that's 0.2. So 0 to 1. And from 1 to 2, that'll be 0.7. 1 to 2, 0.7. 2 to 4, 0.9. 2 to 4 will be 0.9. And after greater than 4, I have 1. First, let's see this. Get more. Okay, you can check if this CDF is valid or not. Non-decreasing. Okay, if it's non-decreasing, and it's between 0 and 1. And we observe that we have a gap. We have a gap, that means that at that point I have the probability. Okay, once I have a gap, then I have a probability at that specific point. Otherwise, the probability of the specific point should be 0 because it's continuous. But if I have a discontinuity, then I should have a PDF in this 4 points. So we can mention that this is a gap, 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 and gap. So to find the PDF, we only need to consider, because when I take the derivative of this constant, it'll be all 0. Right? Actually, it'll be all 0. But we know that only for those 4 points, I should have a PDF. I should have the PDF. So first, let's see what is the probability of x equals 0. X equals 0. That means 0. The gap. So 0.2 minus 0, that's 0.2. Which is also, because you can see this is like a discrete. So it is a PMF at 0. probability of x equals 1. That's 0.7 minus 0.2. That'll be 0.5. And it is also the PMF at 1. Probability of x equals 2. That's 0.9 minus 0.7. That's 0.2. And then the last one is when x is equal to 4. That'll be 1 minus 0.9. That'll be 0.1. Let's see some common continuous random variables. The first one is a uniform random variable. What is a uniform random variable? We say x is a continuous uniform random variable. Then the PDF here. X is between a and b, then the PDF will be 1 over b and b minus a. It's a constant. And AB is the interval that my random variable x is defined. Otherwise, there's no PDF. We say that x is uniform AB. That means x is drawn from the uniform distribution on an interval a to b. So for the PDF, we can draw the PDF. From A to B. And then the value is 1 over B minus A. To find the expectation, consider all possible outcomes times their weightings, which is the PDF. I didn't notice that it should be dx. Okay, so it should be a plus b divided by 2. And for the variance will be b minus a squared divided by 2. You can practice, you can derive it at home by yourself, but on the exam, I will also provide you the table. Okay, so I'll provide you the common discrete random variables and also continuous random variables, the tables with their PDF, PMF, or expectation variance. The next one is exponential random variable. So for the exponential random variable, the PDF looks like this. And lambda is a parameter. Okay, and I only have values when x is greater than 0. Otherwise, no. And we write exponential lambda to say that x is drawn from the exponential distribution of the parameter lambda. So we can plot the PDF. Okay, PDF could be, here's lambda, here's the lambda. When lambda is small, and when lambda is large, lambda small and lambda large, but it is exponential. Okay, so you can expect how it looks like. Let's find the expectation. Consider all possible outcomes times their corresponding weightings. Here we have values from 0 to infinity. Lambda x times e to the minus lambda x dx. And then this is equal to 0 to infinity minus x d e to the minus lambda x. Let's do the integration by parts. So here, integration by parts. U dv equals uv minus v du. That equals uv, so minus x e to the minus lambda x. Your x is from 0 to infinity. Minus the integration v du e to the minus lambda x du, so d minus x. So you have 0 plus minus 1 over lambda e to the minus lambda x. And your x is from 0 to infinity. That gives you 1 over lambda. Then the variance. To find the variance, we know variance is the second moment minus the first moment squared. So we want to find the second moment. You see here. So let's see the second moment first. The expectation of x squared. Consider all possible function of outcomes. Let's choose x squared times their corresponding weightings, which is the PDF. Then you have, I only have values when x is greater than 0. So 0 to infinity, lambda x squared e to the minus lambda x dx. Integration by parts. I think we need to do the integration by parts twice. So first one will be x from 0 to infinity and then plus v du e to the minus lambda x times 2x dx. Now here we go back to this similar type. So we'll do another integration by parts. Then you will have 0 plus 2 over lambda. Integration from 0 to infinity, x times lambda e to the minus lambda x dx. Then I would like to ask you, what is this integration? 0 to infinity, x times lambda e to the minus lambda x dx. That's here, right? This is the expectation of your exponential random variable. So this is, you don't need one. So also in this case, you don't need to do the integration by parts because we know this is the expectation of x, and we found that this is 1 over lambda. So this is 2 over lambda times 1 over lambda. That is 1 over lambda squared. Therefore, your variance 2 over lambda squared minus 1 over lambda. Oh, also lambda squared, so it should be 1 over lambda squared. 2 over lambda squared. So that's why the second moment, 2 over lambda squared. First moment, 1 over lambda, and by any squared. So finally, the variance is 1 over lambda squared. The next random variable is Gaussian. Okay, people use Gaussian random variable a lot. What is Gaussian random variable? The PDF is here. I have mean and variance. Mu and sigma square are the parameters of the distribution. So we can write it down. X, like in Gaussian random variable or Gaussian distribution. Sometimes we also write it down. It is like a normal distribution, n. And we said that x is drawn from the Gaussian distribution. With the parameter, we need two parameters, mu and sigma squared. And for their expectation, consider all possible outcomes times their corresponding weightings. Then we have a bunch of stuff inside the interval. Okay. Now we can change the variable to find the mean. Or if I change variable, let's say that y equals x minus mu. Okay, so this becomes y squared. So when y is minus x minus mu, then the integration dy equals dx. So y is still from minus infinity to infinity. And here we have y plus mu over square root of 2 pi sigma squared e to the minus y squared over 2 sigma squared dy. So we have two parts, y and also u. So let's see these two parts. Y over square root of 2 pi sigma squared e to the minus y squared divided by 2 sigma squared dy. And the second one, mu divided by square root of the square root of 2 pi sigma squared e to the minus y squared over 2 sigma squared dy. So what is this integration? First, let's see this function. You can verify that this function is an odd function. And if this is an odd function, we do the integration from minus infinity to infinity. It goes to 0. So this function is odd. How about the second term? For the second term, I can put u outside, mu outside, and then I have, let's rewrite it. So for this integration, let's see what is this integration. What is the result of this integration? We should know. Okay, see this integration. This is the PDF of Gaussian, right? So Gaussian PDF, you do the integration from -infinity to infinity of your PDF. What is this? By the property of the PDF, this is 1. Because this is Gaussian PDF. And also for the PDF property, if you do the integration from -infinity to infinity, there'll be 1. So that's why you have the expectation that equals mu. And since we learn probability and we know PDF, so we know this property. This integration is 1. But when you took calculus, they also have another proof that is 1. Say, I have the integration from -infinity to infinity, 1 over square root of 2 pi times e to the minus x squared over 2 dx. This integration times the same integration, but I just use different dummy variable. Here we have y squared. So 1 over square root of 2 pi times e to the minus y squared over 2 dy. So this is 1 over 2 pi times e to the minus x squared plus y squared over 2 dx dy. How do we do this integration? We change the variable to Rn theta. So we can let x equals r cosine theta and y equals r sine theta. And then we need a Jacobian. For the Jacobian, partial x, partial r. Here partial y, partial r. Partial x, partial theta, and partial y, partial theta. Here cosine theta minus r sine theta, sine theta, and r cosine theta. So then we continue for our integration. This becomes the integration from, for theta, 0 to 2 pi. For the radius, 0 to infinity. 1 over 2 pi e to the minus r squared over 2 times r dr d theta. So you get r times e to the minus r squared over 2 dr. then minus e to the minus r squared over 2. Then r is from 0 to infinity. That gives you 1. Okay, and then for the Gaussian distribution, sometimes you will see the standard Gaussian. So what is standard Gaussian? If I have the PDF, it should be f of x. The PDF f of x equals 1 over the square root of 2 pi times e to the minus x squared over 2. This is called standard Gaussian, or we say standard normal, because the mean is 0. There's no mean, like x minus mu. Now the mu is 0, and the variance is 1. Okay, and in this case, we can define the phi this form. So for this phi function, wow, it's 1 over square root of 2 pi, and we do the integration from minus infinity to y, because it's a function of y. That means when I plot this normal distribution, we use green. Oh, we use blue. Here I have y. Then this will be phi over y. Why are we interested in this phi function? Because we have a table for this. Okay, it's more convenient. Because we can use table. So how do I get this standard Gaussian? For example, if I have this integration, for this integration, we just change the variables. Okay. That right here, that x prime equals x minus mu divided by sigma, which means if I say x prime equals x minus mu divided by sigma, and x equals y, then x prime will be equal to y minus mu over sigma. Then we have 1 over square root of 2 pi y minus mu over sigma e to the minus x prime squared over 2 dx prime. Then you can see if x is normal distribution with mean mu and variance sigma squared, then the random variable y equals x minus mu over sigma will be the standard normal. And you can easily show that the mean is 0 and the variance is 1. The mean is 0 and the variance is 1. Let's just see this example and then we can finish today's lecture. I have a signal. I either send 1 or minus 1. And the probability are both the same, 1/2. So let me plot this. I send a signal X to the channel. So here's a channel. I send the signal to a channel, and also in the channel I may have some noise. This noise is N and U. And then noise is a Gaussian distribution with 0 mean and sigma squared. Then my output will be Y equals X plus the noise N. Here's the detection rules. If I receive +1, that means Y is greater than 0 or equal to 0. If Y is less than 0, then I will say it is -1. Okay, I send 1 or -1 to this channel, and once my Y is greater than or equal to 0, then I will say I receive 1, +1. If Y is less than 0, then I say I receive -1. Then I want to find the probability of error. Probability of error means that I sent 1, but finally I decided it is -1. I sent -1 and I say, oh, actually it is +1. Okay. So probability of error is when X is 1 is sent, then we say Y is less than 0, not greater than 0. So Y less than 0 under the condition X is +1 that is sent. Okay, and if I send X is equals 1, then this probability here I also need to include. And also the other scenario is that Y is greater than or equal to 0, but actually -1 is sent. So I also need to know that what's the probability of -1 is sent. So remember that for this condition, that means now under the condition X is 1, so Y actually is 1 plus the noise N. So the expectation of Y will be the expectation of X plus expectation of N. So it is 1. And the variance is the variance of 1 plus N. So that is variance of N, and we know N is Gaussian, so this is sigma squared. And the other case, y is equal to 1 minus 1 plus n. So the expectation of y will be minus 1. Because n is noise, the mean is 0. Okay. So now for that probability error, I get 1/2 from minus infinity to 0 because y is less than 0. Oh, and also, how do I know what y is? Which distribution? Under this condition, we know that y equals 1 plus n, right? And we know n is normal distribution. Normal distribution plus a constant. And definitely y is also the normal distribution. In this case, okay, otherwise, what is the distribution of y? We don't know until we have the condition. Because I have a condition, this is not a random variable anymore. This is a constant, either 1 or minus 1. So for this probability, then I have the PDF. This PDF is Gaussian. Okay, Gaussian with the mean 1 and the variance sigma squared. 1 over square root of 2 pi sigma squared e to the mean is 1. So 1 minus 1 squared over 2 sigma squared. Another one, it is also Gaussian when x is minus 1. So y is greater than 0. So this should be 0 to infinity. 1 over square root of 2 pi. Sigma squared e to the minus y plus 1 squared over 2 sigma squared dy. And we can write it down this as a phi function with mean 1 and over the sigma. Okay, and then we can simplify it. And for minus 1 over sigma, same thing for the probability, a PDF property. It should be 1 minus phi, 1 over sigma. So overall is 1 minus phi, 1 over sigma. Let's plot x is 1, x is minus 1 here. And also x is 1. And I want all these. So for all here and above 1, the left hand side is phi of minus 1 over sigma. And right hand side is 1 over minus phi of 1 over sigma. It's a symmetric, so this part is equal to this.